All right, so today will be a short introduction to machine learning. The goal of today's lecture is not to give you like the latest or fanciest machine learning models, but rather give you an overview over the problems and the approaches that are common in machine learning. So we're going to talk about what is machine learning. We're going to talk about overfitting and the bias versus variance trade-off, which is kind of a fundamental problem to deal with in machine learning. Then I will show you how to use some of these approaches in R, specifically in the tidyverse. And then we'll talk about high dimensional data, like what are the problems with high dimensional data, and shrinkage methods as one way of dealing with those problems. So what is machine learning? So far in your statistics education, especially in econometrics, you've probably just been concerned with causal inference. So basically we have been interested in knowing what is, or estimating what is the marginal effect of a variable x on an outcome y. So if you change x slightly, how much does y change? And we rarely paid much attention to kind of how well does our model fit, what is the R squared or so. And in fact, we've actually happily traded off fit of the model against a more credible causal estimate. For example, if you think about IV or instrumental variable regressions, the R square of these models will be low. In machine learning, however, we are generally more interested in approximating the function that describes the relationship, kind of for prediction or classification purposes. And we're not that much interested in interpreting the marginal effect of a single variable, and therefore we can also build models that are more complex, that are kind of nonlinear, and sometimes the individual components are impossible to interpret. For example, if you're thinking about neural networks, like it's not possible to interpret the marginal effect of a single input in such a complex model. And within machine learning, broadly, our problems are in two fields. Like one is called supervised learning, and here's basically our job to we observe certain outcomes for a training data set, and then we try to find predictors and combine them into a model in a way that predicts the outcome in a training data set very well, and then use this on a new data set to predict outcomes for observations where we don't know the outcomes before. The other problem is unsupervised learning, which is kind of grouping together observations where we do not observe the outcomes. So since we don't know the outcomes, we cannot really train like a classifier or something. So what we do is we just kind of group observations by different characteristics and behaviors that we observe, but the ultimate outcome that we are interested in might not be observable at all. So a good example is, for example, if you're trying to rank politicians from a left to right spectrum, since the left to right spectrum is kind of a theoretical concept, and you can't really, like, there is no observable measure in each that each politician has of where exactly they lay on the spectrum, but we can kind of group politicians together by like how they vote, or how their campaign looks like, and we can say, okay, this politician is like very far to the left, this politician is very far to the right, and others are somewhere in between, and you kind of group them together by how are they voting, which party do they belong to, what is their opinion on certain issues, and so on. So one of the main problems in machine learning is overfitting. And kind of to give you an example, we try to build a model that tries to approximate the function f that describes the relationship between all these input variables and the output variable. However, whenever we build such a model, we want this model to have external validity. In a sense, it should not only work on the data set that we're training it on, but it should also work on a new data set. So if we try to predict like whether or not a credit card holder is going to default on his debt. We can build a very complex model that explains everything in the training data set, but then it on a new data set it completely fails because it was just overfitting. And here you can see an example that I've generated myself, but you can see like 3 different models for this data, and clearly the blue line is like inadequate. It really misses like a lot of the parabola shape of this relationship. On the other hand, the green one seems to be inadequate as well, because even though it gets kind of the parabola shape, it just picks up all this noise that is probably not very informative. So if you want to predict on a new data set, like it is unclear why a observation at a certain point should be much lower than one very close to it. And it seems like the red model here is kind of a good middle ground between these models, and we can also expect that this model is probably going to do a good job if we apply it to a new data set. And the idea, like here, that I want to talk about is kind of this idea that you should sometimes accept like a small bias. So the green model, obviously, it controls for many more things, and therefore we have less of a problem with, let's say, omitted variable bias or misspecification of the model. But on the other hand, the variance of the coefficients is also quite large because we're estimating a lot of models. So this one here is a very high order polynomial. And in contrast, the red one is just a quadratic polynomial, where the coefficients have much less variance and much more precisely estimated. So the same idea is kind of, if you like this graph that I like very much because it kind of illustrates the point very nicely, that ideally we would like to have our model to be the left upper corner. We want to have it like low variance and low bias. So it should always shoot in the middle, and the dispersion should be very low so that it really always hits the bullseye. However, like this is usually not what we get in reality, but rather we somehow have to choose between the high variance low bias version or the high bias low variance version. So we either can try to like control for everything and then kind of get it right in expectation, but the variance will be very large. On the other hand, if we say that we're willing to accept a small bias, we know that, okay, our model will be slightly off on average, but it will be very low variance, and it will always give us very very average predictions, but at least they're like consistently not too bad. Whereas here, every once in a while, you might be like completely off. And of course, you want to avoid the high variance, high bias situation down here, because here we get it wrong on average and it has very large dispersion. So in practical applications, like you have to somehow select a model. And in economics, usually we are kind of in the situation where we have rather few variables and somehow even a theory of what we should want to control for. But in practical machine learning problems, that might not be the case. You might have like a very large number of variables to choose from. And then one way of kind of choosing an adequate model is simply to sort of go by an algorithm, right? And so, for example, this would be like one could use like a stepwise algorithm you start with a very simple model and you just add variables to this, and every variable that you add the variable that adds the most in explaining the variance, and then you kind of create one optimal model for each number of covariance, and then afterwards you test which one of these models fits best. Or the opposite approach would be you start with a very large model and then you kind of trim the model down to a smaller model that kind of gives you a good out of sample prediction. The problem is just that these algorithms are kind of greedy algorithms, which means that they optimize very locally. They might miss kind of the global optimum of what will be the optimal set of covariance, because they just like try to find what is the best model with one extra variable, and they don't look at all the possible combinations of variables, and they might miss the optimum, therefore. So also that if you have different such algorithms, they might not give you the same optimal models, and more importantly, these algorithms fail when the number of covariates is larger than the number of observations. And this is the situation where we talk about high dimensionality, and we'll talk about this more detailed later today. So since we want to avoid the problem that our model is overfitting, that the model only fits on our current training data or our current estimation data and does not explain anything outside of this data, a very useful method is resampling methods. And the idea behind resampling methods is that if you would just use like one draw from the distribution, then you always have this sampling variance, right? That just by chance you pick up more observations that have a certain outcomes than others, and so on. And therefore, if you try to fit a model that predicts perfectly the sample you drew from the population, you're very likely going to build a model that is very useless outside of, if you would draw a new sample from the population, you have a different sampling variance, and the model that you built to fit perfectly on your original data set does not work there anymore at all. And so resampling methods is a concept where you basically you estimate a model on a lot of different subsets. So instead of just estimating it on one data set, you draw smaller subsets of this data, and every time you estimate the model again. And the goal is basically to find a model that performs well on average on all of these subsets. And then, since on average, kind of the variance that you get from drawing a small sample should average out, and therefore a model that performs well on all of these subsamples should perform well on a new data set, on a new sample from the population. And so two applications are cross-validations, which we're going to talk about today, but also bootstrapping, which you might have seen, for example, to estimate standard errors. You can, instead of estimating the standard errors with the theoretical formula, you can also just repeatedly draw small samples from your data set and estimate the model, and therefore kind of get the full distribution of the model coefficients. We will not talk about bootstrapping today. So I've been already mentioning the idea of a training data set, and kind of the most common approach in machine learning is the so-called validation set approach. And what this means is that once we have identified a candidate or set of candidate models that we want to test, we split our data into a training data set and a testing data set. And we only use the training data set to select our best model. And the training data set will be held out until the very last step. So what we want to do is a desirable model should fit the training data well without overfitting. So we should not just choose based only on the R squared. And then, like, once we have decided on a model that provides like a good trade-off between bias and variance in the training data set, we then test it on the part of the sample that we held out. But of course, the question is, how do we actually find a good model in the training data set that we can expect to perform well in the testing data set? And this is where we use cross-validation. Cross-validation is the process of splitting the training data further into training data set and validation data set. So in the first step, we split the data into a training data and a test data. And then we do, for example, a 5-fold cross-validation. So 5 times we split the data into 5 components, where we use 4 to estimate the data and the 5th one to validate it. And then we just change the one we hold out. So now in the second step, we use the subset 1, 3, 4, and 5 to estimate the data, and we test it on 5. And then finally, the model that we select is the model that will have the lowest prediction error on all of these 5 folds. And after we have selected it here, we then apply it to the test data. And the reason why we never look at the test data is because also if you're trying a lot of different models, even though inside here you're only estimating it on these 4 subsets and you're holding out the 5th one, since you're doing this repeatedly and for different models, you might still create a model that overfits simply because you're just trying so many different models on all of these splits. And therefore, we always need to keep one part of the data completely out of the selection process to actually see how well the model does.